morning. My name is Milla Kibble. I'm the Deputy Director here at the Isaac Newton Institute. The Isaac Newton Institute is an international research centre specialising in mathematical sciences, and we're delighted to welcome you here to the Institute today as part of the Cambridge Festival. And welcome to everyone online as well. And now it's my absolute pleasure to introduce Professor Marcus du Sautoy. Marcus is a Simonyi Professor for the Public Understanding of Science and Professor of Mathematics at the University of Oxford. He is a world-renowned mathematician, author and broadcaster, widely known for his work in making complex mathematical ideas accessible and engaging for the public. Marcus's research focuses on number theory and group theory, but is equally celebrated for his exploration of the hidden mathematics in music, art and creativity. Today's talk is based on his new books, Blueprints, How Mathematics Shapes Creativity, and he will be exploring the hidden mathematics that underpins the creative arts, from music and architecture to literature, showing us how mathematical structures act as invisible blueprints for human expression. We'll have 1 hour roughly of talks, about 45 minutes say, and then followed by question and answers. And then immediately after that, there'll be a book signing just outside. And you can continue to talk with Marcus then for any additional questions that you may have. So please join me in wishing a very warm welcome to Professor Marcus du Sautoy.
When we're at school, we're often asked to make a choice. Is it Shakespeare or the second law of thermodynamics? Is it Debussy or DNA? Is it Rubens or relativity? Are you going to be the artistic route, the humanities route, or are you going to go the scientific route? When I went up to secondary school, I was kind of very frustrated by this kind of desire of our education system somehow for us to make these choices between the two. When I went up to secondary school, I was starting to do science for the first time, experiments in the lab, dissecting a rat, finding out what's inside that, understanding where we're going to in this universe, where we've come from. I fell in love with the power of science to kind of understand the story of our universe. But at the same time, I was also getting very excited by the arts. I remember my music teacher in our school asked, would anyone like to learn a musical instrument? I was about 11, and three of us put up our hands, and we were taken into the storeroom cupboard, which was pretty bare except for 3 trumpets stacked on top of each other. So we all learnt the trumpet. I did quite a lot of theatre. I enjoyed doing theatre in my school. And so as time went on and the kind of education system seemed to try and push us in one direction or the other, I found it frustrating because I was enjoying kind of both camps. But then I think the thing which saved me was an intervention of my maths teacher at my school, who, in the middle of a lesson, pointed at me and said, "Du Sautoy, I want to see you after the class." And he was a dour Scot. Actually, we were all terrified of Mr. Baleson. And he took me around the back of the maths block at the end of the lesson, and I thought, oh, I'm really in trouble now. Which is where he smoked his break time cigar because they wouldn't let him smoke it in the common room. And he said, "Du Sautoy, I think you should find out what mathematics is really about, because it isn't really what we're doing in the classroom. That's a kind of sines and cosines and quadratic equations. It's something much more beautiful and exciting and full of stories and adventures." And he recommended a few books to me, which he hoped would kind of open up the real world of mathematics. And I remember we went that weekend. I grew up around Oxfordshire. We went to Oxford. Blackwell's is this kind of it's kind of a TARDIS of a bookshop. It looks tiny from the front, but you go in and it's absolutely enormous on the inside. And we found these books. But there was one book in particular that he recommended that made a big impact on me. And this was actually by a Cambridge mathematician, although he also spent time at my college in Oxford, New College. And I think he was in New College when he wrote this book, A Mathematician's Apology. And this was a book about being a mathematician as much as about mathematics, probably more about being a mathematician. And the way he described what he felt a mathematician was surprised me and actually resonated with my desire to sort of be part of the science world and the art world. He wrote, "A mathematician, like a painter or a poet, is a maker of patterns. I'm only interested in mathematics as a creative art." And he gave there are two little proofs in that book, which are kind of little stories about prime numbers and one about the irrationality of the square root of 2, but they are like little stories. And this book kind of opened up my eyes to the fact that mathematics is this wonderful bridge between the world of creative arts, patterns, being a poet or a painter is like that, and yet clearly mathematics is it's the language of nature, it's the language of science, which helps us to understand the two. So it kind of set me off on this trajectory to become a mathematician. And I've spent a lot of time, I mean, I'm a professional mathematician in Oxford, but I've spent over the years many interactions with creative artists, maintaining my love of music, visual art, architecture, theatre, and I began to realize that there is such a strong connection between these two, because time and again when I did events or workshops or creative pieces with people from the creative arts, the sort of things that they were interested in, they were structures that I recognize as pieces of mathematics. And they didn't understand that they said, "Oh, I didn't think this was maths." I said, "No, that is a structure that I absolutely recognize is a piece of mathematics." And it made me realize that this word structure is the key to the connection between these two. Because any artist really loves a structure within which to work and be pushed and pulled around. Whilst if I was going to define the topic of mathematics, I would define it as the study of structure. That is what we do. I mean, it's not arithmetic or long division to lots of decimal places, which is what I think most people think my research is. But it's about structure. It's about that word pattern. It's about understanding the structures around us. And that word structure is very important to an artist. Here's Stravinsky saying, "I can only be creative under huge constraints." Very often as an artist, if you've got a blank page or a blank stage or a blank stave, it's killing for creativity. Creativity sort of emerges out of creating an interesting structure, which then pushes and pulls you around. And Stravinsky is one of those who recognized very clearly the power of mathematics as a useful language for him as a composer. He wrote, "The musician should find in mathematics a study as useful to him as the learning of another language is to a poet. Mathematics swims seductively just below the surface." But what I'll show you is that sometimes you get a composer like Stravinsky, who really understands the mathematics, is kind of using that to push his creativity. But quite often you find a composer or a visual artist who is just interested in a structure for its aesthetic sense and almost discovers mathematics through that sense of aesthetic journey. So often they don't know that they're actually rediscovering or sometimes discovering for the first time a piece of mathematics. Anyway, this realization of the word structure as an important connection between the creative arts and mathematics set me off on this journey. As I say, I've been, for many decades, been working with many artists. It's kind of been my downtime, but I thought, actually, I should bring the stories together of all this interactions I've had. And so I just recently wrote this book, Blueprints, How Mathematics Shapes Creativity, to explore some of the connections between these two worlds. And I sort of framed it around the structure of the book is kind of 9 structures of mathematics. And each of those structures I then kind of use as a launch pad for exploring how different artists may have realized these structures in their work. It's kind of interesting because my first instinct in writing this book is, people, I think it was Stephen Hawking who said, every bit of maths you put in a book halves your readership or halves your sales, more importantly. So I thought, maybe I need to put the kind of art first and then let the maths bleed in. So I was thinking of structuring the book sort of around architecture, literature, music. But then I did this flip and I've actually put the maths kind of first, the structures there. And it turned out to be a much more interesting way to write this book, partly because what was so interesting was to take a structure and then to see how each of the different artistic disciplines realize this structure in such varying ways. How does a musician react as opposed to an architect, to go from the oral to the visual? For me, it was a much more exciting way to write this book, to start with the mathematics. But actually, that said, I actually start each chapter with a story of an artist who's used that particular structure in their work to then reveal the structure itself. Yes, I was going to say that if I was going to, we got that kind of 9-sided figure as one blueprint for the book. But the other blueprint I think I would have for the book is a triangle. And we've already seen 2 of the corners of this triangle, mathematics and the creative arts. But that word structure, very often the structures that we find really exciting, both as artists and mathematicians, already have their origins in the third point of this triangle, which is nature. Those structures are very often already embedded in the natural world, in the way the universe has evolved. And I think that's the musician or the creative artist is very often reacting to structures around them in nature. And mathematics too. Mathematics grew up as the language, 5,000 years ago for us to understand, navigate, manipulate our environment around us. So perhaps it's not surprising that the structures that we are both interested in already have their origins as things we are seeing around us, outside in the natural world. Let me take you to the first blueprint. I'm going to give you a little flavor of 3 of the blueprints in the book. And I've used this word blueprint as the kind of idea of a structure, some sort of underlying skeleton which you flesh out in different ways. So the first is actually, in some sense, the blueprint for the whole of mathematics. Out of prime numbers, these indivisible numbers, we get all numbers. From numbers, you get mathematics. From mathematics, you get the universe. So these are really the blueprints of it all, these indivisible numbers. And so, as I said, I start with a story of an artist who interestingly used this structure in their work. So I've started actually with a composer, one of my favorite composers, Olivier Messiaen, French composer. I actually encountered him for the very first time. I used to play in my local youth orchestra in Oxford. I used to spend every weekend on a Saturday going up to play in the orchestra. And then there was one weekend when the conductor from the London Sinfonietta brought the score to Tarangalila Symphony, which is this incredible kind of orgasmic piece of music for full orchestra, amazing trumpet parts. I think my trumpet playing was at its peak that Saturday. It's gone down ever since, and it had to be able to play this piece. But I was absolutely blown away by this piece, and so it set me off on this kind of journey to explore other pieces that Messiaen had written. I didn't realize at that point that actually Messiaen is somebody who has a lot of interesting mathematical structures in his work, and he comes up quite often in the book in different blueprints. But there's one piece that I fell in love with, where I went to our public library, had a kind of record library, and I took out a piece called The Quartet for the End of Time. This is one of the most iconic pieces of the 20th century, partly because of the story of where it was first performed, because Olivier Messiaen composed this piece while he was a prisoner of war in Stalag 8A during the Second World War. And he discovered, he played piano, he discovered there was a clarinetist in the prison camp, a violinist and a cellist. And he wrote this piece, The Quartet for the End of Time, for the 4 of them. There was a rickety upright piano, and they performed it in January 1941, and the description of the concert is extraordinary because most of the people in the prison of war camp had never been to a classical music concert before, yet it said they were blown away by the performance of this piece. It was, this is January, and apparently there was snow everywhere, and the temperature was incredibly low, but the music was incredible. It starts with a piece called the Liturgie de Cristal. And it's in this piece where later I discovered there's an amazing use of prime numbers to create a very strange effect. I wasn't aware of it when I first listened and fell in love with this piece of music. But then to discover that the other thing I love, mathematics, was actually sitting at the heart of this piece was extraordinary. So the piece starts off with the clarinet and the violin exchanging bird themes. So Messiaen was very interested in kind of notating bird themes. But then it's in the piano part, the part that Messiaen was playing, where there's an amazing bit of maths at work. So Messiaen has a 17-note rhythm sequence, which just repeats itself over and over again. So it starts off crotchet, 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 then it goes into this lovely syncopated rhythm, and then ends crotchet minim, and then this is where it starts again. It just repeats the same rhythm. Crotchet, 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 syncopated rhythm, crotchet, minim. And this just goes on, rhythm. So it could be really boring, the same rhythm just repeated over and over again. But the harmonic sequence does something different. There are 29 chords, which are just, again, 29 chords bashed out, then he repeats the 29 chords. The 29 chords goes up to this last place here, and then you see the same chords just repeated over and over. So again, it could have been really boring, but it's the interaction of these two which is really interesting because, of course, once the rhythm starts again, the chords are working their way through the 29 chords. When the 29 chords start again, they're played in a completely different rhythm to the first time you heard them. And so you have to hear 29 times 17 chords before the thing comes back and starts to genuinely repeat itself, by which time the piece is finished. So, and actually, if you think about it, it's called the Quartet for the End of Time. And I don't know whether Messiaen thought about, I mean, I think it was, it was a time when, history seemed to be blowing apart, Europe seemed to be blowing apart. But actually, if you think about it, to keep track of time, you need something that repeats. We only understand time because of seeing a pattern. Maybe it's the cycle of the going around the sun or the moon or a heartbeat or a drip. This has nothing which repeats. So it's almost as if time has vanished because there is no repetition. Although, of course, it's built out of repetition. The interesting thing is the choice of numbers, 17 and 29. Two prime numbers, two indivisible numbers, and it's the fact of them being indivisible that means that they never kind of get in sync before you've heard 17 times 29 chords. Imagine if you'd chosen 15 and 30. Well, it would repeat itself after 2 15s is 30, and you get it repeating almost immediately. So Messiaen very carefully chose these numbers to create this effect of kind of two cogs which never kind of repeat until they've each gone round the respective number of times. I'm going to play you a little bit of the music so you can hear the primes at work. So here's the beginning of the Liturgie de Cristal. And now the rhythm repeats, but the chords are still working their way through the 29 chords. And now the chords start repeating, but in a completely different rhythm. Now, I was kind of intrigued. How much mathematics did Messiaen know? Did he know exactly what he was doing when he chose these numbers? And I had the chance to talk to George Benjamin, composer who, as a very young man, worked with Messiaen. I asked him, what was his mathematical training? And he said Messiaen had no mathematical training. He just almost discovered the power of these indivisible numbers to keep things out of sync through his own kind of aesthetic journey. And actually, there's a lot, as I say, of different structures that Messiaen uses. He creates some very interesting new scale structures using kind of the world of symmetry. But it seems like he was kind of intuitively drawn to these numbers for their power. There's another use of the kind of primes in kind of more contemporary music, which I was intrigued by, which is Radiohead, which is I discovered that Johnny Greenwood is the guy who writes most of the really interesting music that Radiohead plays. Johnny Greenwood here. I was very intrigued to discover that he too played in his local youth orchestra, and he too had the chance to listen to, or play some Messiaen in his youth orchestra. I don't think it was the same. We weren't at the same time. So, but it seems like he's a big Messiaen fan, and you can hear that in the Radiohead music, because they love, most pop music just comes in four groups of four, and it's incredibly boring. And but Radiohead's music varies from 5s to 6s to 4s to 7s, and there's everything in its right place, which is really kind of a joke because it's all in the wrong places. You try and dance to the following piece of music. It's almost impossible, because if you look at the score, it's just moving between, you think you've got 5, and then it seems to be in groups of 3, and then it's in back to 4s. This piece is a beautiful example of the use of primes to create a really unsettling effect. We'll dance to it later. So I said that very often these structures first appear in the natural world. Prime numbers, clearly Fibonacci numbers are in this book, because they're one of the structures artists love, and Fibonacci numbers are connected with the natural world. But primes is quite a challenge, actually. But there's a wonderful example of absolutely the same trick that Messiaen used in the natural world already, which is this strange prime number cicada, which lives in the forest in North America. This is my favorite insect of all time. If I had to take one insect with me on a desert island, it would be this cicada, because it's such a cool cicada. It has this weird life cycle. It hides underground, doing absolutely nothing for 17 years. And then in the 17th year, they all emerge from the ground almost on the same day. They fill the trees. They sing away, or at least half of them do. The males sing to the females. The sound of the forest is so loud that residents move out very often for this 17th year. There's even a website you can check if you're getting married that summer, are the cicadas, because you won't be able to hear anything your guests say. They party away, they mate, they lay eggs, and then they all die. It's actually quite dangerous, because there's so many cicadas all over the roads and things. People are planing on these cicadas. Then the forest goes quiet again for another 17 years. Now, 17, that prime number that Messiaen used, is that just a coincidence? Well, it seems not, because there's another species of cicada which has a 13-year life cycle, and you never find cicadas with a 12, 14, 15, 16, or 18-year life cycle. So something is helping these cicadas about the prime numbers. And we believe it's exactly that same trick that Messiaen was using. Prime numbers allow you to keep it out of sync, and in this case, out of sync of a predator that used to appear periodically in the forest as well. We believe, this is our best hypothesis. Let's suppose a predator appears every 6 years in the forest. If we take a cicada which appears every 9 years, we get them coinciding quite quickly, just like the Messiaen, if he chosen 15 and 30. Already the second time the cicada emerges, there are predators there. So the fact that 9 is not prime is kind of not helping it to keep away from the predator. But if we change the cicada to a 7-year life cycle, a prime number, it's appearing more often than the forest. You might think, well, it's got more chance to be eaten up. But no, that prime number keeps the cicada out of sync of the predator, and they only meet for the first time. The first number divisible by 7 and 6 is 42. So that gives them a much better chance of surviving in the forest. So it seems like there was some sort of competition between these two. Maybe the predator shifted, found the cicada's life cycle. The cicada had to adapt and change, and the cicadas got up to 17 in some of the forests in North America. The predator, who didn't know its maths, died out. Message for you, if you don't know your maths, you die out in this world. And so we've got left with these cicadas with this prime number life cycle. But it's exactly the same. The cicada and the predator is a bit like the rhythm and the harmony in Messiaen's music. So very interesting kind of natural realization of this idea of keeping things out of sync. Now, I suppose music and mathematics have always had a natural affinity. And in fact, I'm going to be part of a program here at the Newton Institute where they're looking at connections between mathematics and music in a few years' time. I think maybe next year. And I suppose it's the idea that music is quite abstract in its quality, so it doesn't naturally translate. So you're interested in the structures in their own right. Pattern is really important. I sometimes say, you know, maths is the science of patterns and music is like the art of patterns, you know, that. But so a little bit more challenging maybe to, what about the world of literature? That seems very polar from kind of opposite to mathematics. But there's an amazing use of prime numbers in literature and a very surprising place in Shakespeare's work. I actually got asked a few years ago to do a talk about maths and Shakespeare. I think it was a Shakespeare anniversary, and I was a bit stumped. I knew no connections between Shakespeare and maths, but the wonderful thing about Oxford and Cambridge is that you know, we get a chance to spend a lot of time with people outside of our disciplines. So at New College, I very often sit next to people doing philosophy, law, history, and that lunchtime I had the chance to sit next to Will Poole, who is an English fellow at New College, expert in Shakespeare and the world around Shakespeare. So I said to Will, I've got to do this talk and I don't know what to talk about. And Will then told me the most extraordinary amount of mathematics that Shakespeare uses actually throughout his work. There's quite interesting use in the later plays. It's about the time that Galileo, Copernicus are putting the sun at the center of the solar system, and you can really see like Cymbeline as a sort of a whole metaphor for putting the sun at the center of the solar system. But it was the use of number that I was fascinated by. What's the most famous line of Shakespeare? Well, yeah, to be or not to be. So you all know that Shakespeare works in iambic pentameter. That's 10 syllables, you know, 5 groups of 2, short, long, short, long, short, long, short, long, short, long. But he doesn't always do that. And when he wants to wake you up, he disrupts that. So this most famous line of Shakespeare, to be or not to be. So count the syllables. To be or not to be, that is the question. It's an 11 syllables. And so that's very disruptive. I mean, things, you know, often poetry comes in 4s or 8s. In fact, the king, just before Shakespeare's time, banned any poetry that had an odd number of syllables as being a thing of the devil. So this was quite a brave thing to do. And, you know, this is an important moment in the play. You're kind of lulled into a kind of like, oh, more iambic pentameter, and you're drifting off. And then suddenly you get this extra beat. And that 11 and that disruptive prime, which somehow doesn't fit into any rhythm, wakes you up. Macbeth, is this the dagger that I see before me? You didn't need the that, but the that causes a disruption because, again, it's 11 syllables. But this isn't the only prime that Shakespeare uses. Whenever there's magic afoot in Shakespeare, it goes down to 7 syllables. So when Puck is administering the love potion into the eyes of the lovers, he says, "Churl, upon thine eyes I throw all the power this charm doth owe." It goes down to 7 syllables. When shall we 3 meet again? Again, 7 syllables. Shakespeare is using these numbers as a very deliberate code to tell you that we are moving into a realm of magic, or to sit up and listen. And he uses this in a lot of places. There was another time, so I played for the England Writers football team, which is this kind of like, and if you've written a couple of books, you get invited along. And we play matches against other writers' teams around the world. So we had this World Cup a few years ago in Germany. I smashed heads with a Swedish novelist, and we spent the whole afternoon in a German hospital with our blood pouring down our heads. But I was in defence, and my other defender was Saul Frampton, who's another professor of English. I can't remember which university he's at, but he's another Shakespeare expert. And you know, there was one point during one of the matches, like, Marcus, I have to tell you about this poem that Shakespeare wrote. It's an allegorical poem. It's a very late one. It's called The Phoenix and the Tortoise. Phoenix and the Turtle, maybe because it's turtle dove. And this is just dripping. When I looked at it, it was like amazing because it's absolutely dripping with prime numbers. The number of stanzas, the stanza, number of lines in the stanzas. Again, it's a lot of 7 syllables. I mean, you don't do that randomly. It was a completely deliberate act. It did cause us to let in a goal because we were chatting away. And then the strikers were, "What the hell are you doing?" We said, "We're discussing Shakespeare." Which seemed, okay, that's fine then. So very interesting to see different, as I said, one of the exciting things was just seeing how different people use these numbers in different ways. Well, perhaps we should move from a kind of numbers to something more geometric. lots of geometry in here, hyperbolic geometry, lots of symmetry. I'm going to take you to the world of fractals because this is, again, a structure that we see a lot around us in nature. But again, there's been quite an inspiration for artists. And the story I start with for this blueprint is an artist who did not know anything about fractals, but ended up actually using them in his painting. So this is Jackson Pollock. Jackson Pollock's paintings, these incredible drip paintings, have sold for some of the largest sums of money at auction of any 20th century painters. Yet, a lot of people think, oh, come on, surely I could do this. Like I'm just flicking paint around. I mean, when our sort of front room in our house after our children have been painting often looks like a Pollock. So, maybe you can fake a Pollock. And I start with this story of a guy who discovered 22 Pollocks in his attic. And he said, oh, yeah, my parents knew Pollock, and very early on in his career, he would exchange paintings for food or things. And so it seems vaguely convincing story, but it was not artists, but mathematicians who revealed that they were, in fact, fakes, because Jackson Pollock is actually doing something very special when he creates these paintings, because they are fractal in quality. So a fractal is this geometric kind of shape that we discovered in the 20th century, which has this property, when you zoom in on it, it never seems to simplify. A lot of geometries may look quite complex to start with, but you zoom in and then they're just really made out of lines and curves. But a fractal, you zoom in and it just never seems to simplify. And that is somehow key to why Pollock's paintings, I think, are so magical, because when you're in front of these huge canvases and you walk towards them, you sort of lose yourself a sense of perspective. You're not quite sure, am I close? How close am I? Because they're kind of scaleless because of this fractal quality. So here are four, well, it's the same Pollock, but I've zoomed in closer and closer, certainly three of these, it's quite hard to tell which one is the original painting and which one is a zoomed in section. Once you're getting to the top right, you're starting to see the paint, and certainly this can't be genuinely fractal because at some point you get the pixelization or whatever. But the others, so the original one is a top left, and it basically you're going around anti-clockwise, zooming in. But you see this kind of, it's very hard to tell if you're in front of it quite how near you are. This fractal quality is something that was not present in the paintings that were found in the attic and were revealed to be a fake. Now, what was Pollock doing that meant that he was able to create this kind of structure? He had a very distinctive painting style. He used to paint quite often when he was drunk, which could have contributed to this. But basically, if I was going to paint and flick paint around, I'd probably go like this, flick, flick, flick. And I create a very regular pendulum, and the result of the geometry would be very regular as well. But Pollock would almost dance as he painted, and he would swing his arm around, both bits of his arm, his shoulder. As I said, he was a bit drunk often when he did this. And what he was creating was something called a chaotic pendulum. And a chaotic pendulum is very unpredictable. And the geometry of chaos, which is what the dynamics of this thing is, a fractal. And so the result is this kind of fractal painting. Now, this gives you a way actually to fake a Pollock, because all you need to do is set up a chaotic pendulum, put a paintbrush on the bottom. So I did this actually, and here's my. I tried to sell this on eBay, but it didn't go for very much. So there's clearly a little bit more to Pollock's work than just a chaotic pendulum. I went actually to visit Pollock's studio in America, and as I said, fractals are the geometry of nature. So much of the way nature grows things have the geometry of a fractal. And you really saw this when you went to Pollock's studio, because it was surrounded by forest. It was winter time when we went. And the trees without the leaves, there's a huge trunk and then a branch and then smaller branches and smaller branches. You have a fractal structure in the way that a tree grows. The smaller bits look like mini versions of the larger tree. And so really Pollock was abstractly capturing the geometry that he saw around him in these paintings. The idea of fractals as a way to generate something which looks like the natural world has been used by other people as well, in particular Pixar Animation. I went and made a visit to their studios on the West Coast. You think that an animation studio is just full of artists, but Pixar, half the people that work at Pixar are mathematicians who understand how to use fractal kind of geometry in order to create wonderful environments. And in particular, the Pixar's Up with all those wonderful jungle scenes. These are all generated using fractal mathematics. More recently, the Marvel universe wanted to create some, not kind of 2D, but sort of real 3D kind of fractal structures. In particular, they wanted to create a planet which had a kind of fractal look to it. And they knew about this thing, the Mandelbrot set. So the Mandelbrot set is this two-dimensional fractal, which you zoom in on this thing and you just see copies of the original thing, new structures appearing. Some of you are old enough probably that you went clubbing in the 90s and we all seemed to dance to these things because it was psychedelic. But so they knew this thing, but they wanted, well, but do you have a three-dimensional version that we can create a planet out of? And it really kind of challenged the mathematicians because the formula, which is quite a simple formula, kind of quadratic formula, which helps you to generate the Mandelbrot set, it just didn't work to create anything interesting in 3 dimensions. And eventually we discovered that if you use a kind of equation which raises things to the power 8 in this equation, you started to get a structure which looked a little bit more interesting and like a 3-dimensional Mandelbrot set. So this is now called the Mandel bulb, created in a similar way to the Mandelbrot set, but it was sort of like perfect for creating some weird planetary environment. If you zoom in on this thing, you find there are little caves and valleys and crevices, and it somehow seems to be multiple copies of the universe itself. And so the Marvel universe latched onto this as like, this is perfect. And so you actually find this being used in the Guardians of the Galaxy 2, which the Ego, the Living Planet, is actually a fractal generated planet. Great, so I'm going to take you, the last structure I want to talk about before we get some time for some questions. It seems a bit like an anti-structure because I'm going to talk about the role of chance and randomness. Now you think almost like, well, that doesn't sound like a structure, that sounds like an anti-structure. But actually we've understood that randomness and chance has lots of patterns inside it. The mathematicians of Fermat and Pascal's time, well, Fermat and Pascal understood that you could mathematize randomness and understand, you know, when something actually has genuine randomness versus perhaps something which has hidden structure in it. But artists have found chance, especially at the beginning of the 20th century, quite an interesting kind of structure to push them in ways that they may not have thought about originally. The story I start with in this chapter is of Jean-Hans Arp, who was getting very frustrated with the sort of the aesthetic world that he'd grown up in, and he just found it very stultifying. This was the beginning of the 20th century. The First World War had just happened. It seemed like all of the politics and the structures of the past had led us to war, and this stimulated artists at the time to say, we need to break this. We need to somehow break out of our structures and do something new. And he was one of the initiators of something called the Dada movement, who really were inspired by the idea of the way that chance can make you do things you never thought of doing before. The way it can make offerings that with your structure of your old structures you've never thought about. And there's a story about how he was getting so frustrated with trying to create something that he ripped up a piece of paper, threw it up in the air and just, I've got no ideas. And then when he came back into the studio some hours later and he saw the way the paper was on the ground, he suddenly thought that is quite an interesting structure, which came out of just the random falling of the pieces. And it started, you know, so collage with squares arranged according to the laws of chance. The interesting thing, of course, is if you use a bit of mathematics, you can tell that he tinkered with this. Because that does not, there's some chance in there, but there would be overlapping. And this is the interesting thing, that tension between, yes, are you going to make that an offering and then take it somewhere else, or are you going to let the chance really be the agent here, and you're going to let the chance have its life? I got invited to the Serpentine Gallery to give a talk one afternoon about Gerhard Richter's exhibition a few years ago, which again claimed to be using chance to generate these interesting canvases where Richter, they were 5 by 5 grids, and he just said, I randomly filled each of the grids with colors. So he had 25 colors inside a bag, and he would pull the color out and then paint that one, put it back in, jumble, blah, blah. And there are 196 canvases, and you can put them together in different ways. So the exhibition at the Serpentine had 10 by 10 grids, so 4 of them were put together, and so it's quite a nice choice of 4,900, the different ways you can put these together. So actually 196 canvases is enough that you can do a bit of statistical analysis. So I was like, okay, did you actually mess around with this? And so I actually did a lot of counting of the colors in all of the 196 canvases. And I discovered that they actually absolutely on the nail hit what you would expect from a random process. So it seems like Richter really didn't interfere with the colors. I had the chance, actually, I work with an artist, Richard Rees, on something called the Pattern Foundry, and he curates lots of interesting patterns. And this is a graphic design project which we made into tiles, which are different colors and different widths of tiles. And this is my kitchen. We're the first place to use these tiles. And I was very excited because I thought, oh, I can do this is just after I'd talked about the Richter exhibition. So I thought, oh, great, I can do a kind of Richter on the tiles in our kitchen. So I thought, all right, so randomness. I'm going to use the decimal, I'm a nerd, so I'm going to use the decimal expansion of pi to code up the colors. And so I had them all laid out according to the decimal expansion of pi, so various numbers with different colors and widths and things. And I had them all laid out. I was like so excited, and my wife came down and said, look, this is how our kitchen's going to look. And she said, no, that's no good. There are 3 reds next to each other. I said, yes, that's the beauty of randomness. It kind of comes things like, she said, no, I'm not having that. Like, so she moved it around. I was like, so you'll see there's no colors next to each other. It's like, oh, so it's very not random, and it's not pi, which is deeply frustrating. But there are some very interesting mathematical kind of questions which come out of often these art projects, which the artist probably was never aware of. One of them is the way you can put these canvases together. Because I started going on this journey of, oh, yeah, okay, so you can have like 196 canvases of 5 by 5, but you could have 10 by 10, so you could put 4 together. But what other ways are there? So they're always square. So it came down to, oh, that's really interesting. How can you write 196 as sums of squares? So, for example, you could have 11 canvases lined up, and then 5 and 5 and 5, 5 by 5. So that's one way you could do it, and that's one of the configurations that Gerhard Richter offers as for the gallery to show their exhibition. Another one, you can do them all as 7 canvases, so 49 squared, 49, 7 squared. So he has, I think, 13 different ways you can do it. And I was like, is that all? So, of course, I started, oh, that's very interesting. So basically you're asking, how many ways are there to write 196 as sums of squares? This is a problem that we love, and it's one that Fermat was interested in. We've been exploring for, the question of what numbers can you write as sums of squares. So it turns out, I think I did a calculation. I didn't include 1 because I felt that was a bit boring, just one as a square. But there are something like 600 odd ways that you can break 196 into sums of squares. So a lot more exhibitions that Richter can do if he wants to. So randomness coming up in art. Even Leonardo actually used to say, I'm stuck for ideas, and there's a story of him throwing a rag at a blank canvas and then seeing the shape that the kind of water made, and that being his inspiration. But the use of randomness has been in art, actually goes back quite far, a long way. Mozart used it to make this this dice game to be able to compose a waltz. So he had 11 different bars of music for the first bar of the waltz, and you would throw your 2 dice, and it would then pick which one, and then you'd go to the second bar, and there was now 11 different bars for the second bar, and you would just randomly keep on doing it. So you felt like you were composing a Mozart waltz using your dice. And of course, the number of possibilities here is huge. I actually did one here. So this little waltz here, this is a piece of Mozart which has never been heard before. This is like would be a premiere if we had a pianist here to play it, because the chance that this has ever been generated out of the dice, it's, if you put them end to end, it would probably take to the end of the universe to play them all, which is kind of interesting. So the game here, in a way, is Mozart being able to choose bars of music such that however the dice land, it sounds good. And a few of the times you can really feel a slight clunk in the connection, but his artistry is to be able to compose such that they work in whatever order. But it does feel a bit frustrating because you want, well, isn't it an artist about making a choice of which of these is actually worth listening to? There's another project in literature which I think is really a very valid use of randomness to communicate an idea, which is B.S. Johnson wrote, he was quite an experimental novelist. He wrote a book called The Unfortunates, which when you get, I went to the Bodleian in Oxford and got out our copy, and it comes in a box because there are 27 chapters, and basically you randomize the chapters, except for the first and last. So the first and last are there, but you read the other 25 in any order. So you'll realize that's 25 pictorial novels. That's a lot of novels. And this story is the story of his memory. He's gone back to cover a football match, and he goes to this town in the Midlands, and he realizes, oh, this is where a friend of his used to live, and his friend had died, and it's his memory during the day of all of the episodes that he had with this person. And that's why I think the randomness is used so well, because memory is a bit random in what order a memory comes to you, and you'll remember something right from the beginning and then a recent thing. And so I think it's a lovely use of randomness, very genuinely to capture the idea of memory. And I read through it in one random order, and it was a really beautiful and moving experience, and a lovely use, I think, of randomness, not just to generate a lot of examples of something, but actually capture the nature of memory. So that's a bit of a flavour of the chance. This is, I think, very much a two-way dialogue. Here's a lot of artists using mathematical structures in their work. But for me as a mathematician, I think one of the reasons that I've spent so much time over the years with creative artists is that I think it helps my mathematics. Because mathematics is a hugely creative subject. We're jumping into the unknown. We're not quite sure what's going to happen next. The inspirations come from very interesting places. So I found the dialogue with artists very stimulating for me in the mathematics that I choose to do. And a lot of people have talked about, we've already heard Hardy talking about mathematics being very creative. Here's Carl Weierstrass, one of the great analysts of the 19th century. A mathematician who is not at the same time something of a poet will never be a full mathematician. That sense of aesthetics is very important for us. We talk about beauty in mathematics. Keats always talked about beauty helping us to understand truth. But beauty is very much at the key of, or at least aesthetics, maybe not beauty. I don't mind ugly mathematics, but I want the mathematics to kind of take me on an interesting journey. For me, a mathematician is a storyteller, and I want the stories of my proofs to surprise my audience, to surprise my readers. Oh, wow, I didn't think those two things were going to be connected. You say they are. Okay, convince me. And you take them on this journey, and there's this kind of moment when you say, whoa, I see them merging and becoming one. So the power of the poetry of the mathematics and the story of it. Pure mathematics, Einstein said, is in its way the poetry of logical ideas. This is one of the things I'm most proud of proving mathematically. I'm not expecting you to understand any of what's on this screen, but this is the discovery of a symmetrical object in very high dimensional space that I made, which connects the world of symmetry with the world of something called elliptic curves, which is still a mystery to us, the strange trying to solve strange curves, a quadratic in y equals a cubic in x. We don't understand these. But nobody expected this world of symmetry to have this connection to the world of elliptic curves. And for me, this is like a story connecting these two realms. And it's the choice that I've made in wanting to tell this story rather than any other story. We're all very, very worried about the impact that AI is going to have on all of our industries. The creative industries are worried, but for me, I feel like this is a very powerful new tool, which might take you in new ways. But for mathematics, it's kind of interesting because it can generate quite a lot of interesting mathematical proofs. But are they really interesting? We have an aesthetic judgment we make on the mathematics, which makes it elevates it just from being a true statement about numbers and geometry to actually something that we want to share with our audiences. I could get my computer now to churn out many symmetrical objects, but most of them will have no interest at all. It's my role as a mathematician to go, no, this one has got an interesting story to it. I'm not saying that AI won't at some point be able to appreciate the aesthetics of what we find an interesting story. But for me, it's that element of choice which makes the mathematician as creative as the creative artist. Anyway, so that's a little guide to 3 of the structures. If you want to find out more, then come and buy a book at the end. But thank you very much for inviting me here to Cambridge.
Open the floor to questions.
Very fast question there. Yeah, great.
So, like, as maths gets more complicated, it becomes more and more abstract, right? Like, say, imaginary numbers, calculus. All of this is really abstract. Like, could you find math in the more, like, can you find art in the more abstract parts of math, or would it have to be more for the simplistic parts?
I think, so did everyone hear that? Would you like me to? So there's some very high level abstract maths which almost doesn't seem to have any physical reality to it. Are we ever going to see those parts of mathematics as something that might interest an artist? And I think very much so, because a lot of art by its nature is quite abstract, and conceptual art, for example. So I think that artists really find exciting something that may not be realizable physically as something to explore. So I'm doing some work with composer Emily Howard. We sent up a centre in the Royal Northern College of Music. So she's a professor and composer there. But she's really interested in the idea of structures that are in my realm, which could stimulate new music for her. So we wrote a string quartet together called 4 Musical Proofs and a Conjecture, because I felt like a proof is, no, seriously, no. A proof is a bit like a piece of music. You start with some themes and then the proof kind of interweaves them. And so she took that as an idea. And they're very abstract kind of ideas, like the proof of the irrationality, the square root of 2. That is, how do you make that into a piece of music? So that was quite an interesting challenge for her. So I think I think artists actually love the challenge of something which isn't so obviously, a Fibonacci number or a golden ratio or something. There was a question down here, and then we'll come to you.
Do you find that there's an inherent conflict, contradiction in maths that you use in a scientific domain, such as physics, versus the artistic mathematics that you're talking about here?
Yes, so the conflict between maths that's used in kind of scientific realm or engineering realm, physical realm, or the maths that's appearing in this kind of creative realm. And actually, of course, G.H. Hardy in A Mathematician's Apology is very snooty about the mathematics that is used by engineering or sciences is the most boring bits of maths, which I think is a little bit unfair. He was quite snobby, and I think he'd be very surprised to find that his very pure world of number theory, of course, is a key to internet cryptography. So I think there's that kind of division. There's much more fluidity between the two. A lot of ideas which look very kind of pure are absolutely key to, in biology, for example, understanding protein folding, the idea of knots, but that's quite an abstract thing. So I think there's a lot more interplay between the two. And as I said, I think often even the very esoteric bits of mathematics probably have their origins in something quite physical and quite natural. And that's often why very pure bits of maths land back down again as things which are absolutely essential to understanding the universe around us. Einstein could not have done his breakthroughs in general relativity had Riemann not kind of just explored high-dimensional geometries of non-Euclidean nature just for the love of it. And you see, one of my chapters is all about hyperbolic geometry. Very interesting. Zaha Hadid uses hyperbolic geometries in her architecture. Emily Howard actually used it in some of hers. And yet, so that seemed a very abstract thing, but it seems to be the shape of our universe is probably one of these geometries. Right, yeah.
Right, so you mentioned towards the end that for the proof there was this aesthetic criterion that distinguishes us from the machines doing the calculations. Kind of following up on that topic, there are certain patterns that even people who are not mathematicians, I find them find particularly appealing. Of course, the Fibonacci sequence, the gold ratio, and so on. But I also noticed, at least from my experience, I'm a particle physicist, so I might be weird, but I noticed, for instance, plots of there's like bifurcation in a chaotic system also find very appealing visually. So why do you think it is? What exactly it is that causes this particular, some specific bits of mathematics to appeal to us more than...
I think it goes back to this idea that the things which light up our brains very often are the things which helped us in an evolutionary way. So very often it's about, am I recognizing something within the natural world which is helping me to kind of survive in some way? So that's why we're super sensitive to symmetry, because when in the jungle, if we saw something with symmetry, that's an animal and it's going to eat you or you could eat it. So the person who couldn't recognize symmetry was the one that got eaten. So I think quite often we are that resonance, and that's why, fractals, you think, well, that seems to be something very complex. But again, we're getting this resonance, I think, and our brain is warming up and calling that, I'm responding to that, I find it beautiful, or because it's resonating with nature. And you can really see that in Pollock's work, because we have this thing called the fractal dimension, which fractals are sort of like shapes between, they're not one-dimensional because they're not lines, but they're not two-dimensional because they're not. So we actually can measure the dimension of how much is it kind of filling the space. And so we have a dimension between 1 and 2 for fractals. Now, the Pollocks that we really love, the ones that just like, are the ones whose fractal dimension is closest to the fractal dimension we often see in nature. And when Pollock kind of dialed it down or up, made it too high fractal, and it wasn't natural, we don't like those ones. They don't sell for as much. So I think that's kind of supports the idea that the sort of things, and golden ratios are because of the way things grow, of course, like that. So I think that that's probably the key for why are our brains lighting up when we see certain structures. It's because they helped us to survive and be where we are today, I suppose. Do you have time for one more? 2 more? I mean, I'm happy to be here all afternoon, but careful, yeah.
The mathematics of nature that you described, do we see that mathematics being consistent across all scales from subatomic all the way up to cosmological?
Oh, that's very interesting. Quite often, yes. For example, the idea of a spiral, we see, on a huge scale, on galactic scale, we see it in the way things grow, and then we can see it on a microscopic scale as well. Platonic solids as well, down at the crystal level, molecular level, diamonds being strong because it's a tetrahedron, but then moving up scale to something like a virus. I mean, again, that's small, but not as small as the sort of molecules of the diamond. So I think that we are seeing these things actually at many different scales. One of the challenges, of course, is maintaining some of these structures. So, like that, the idea of a perfectly symmetrical crystal I went to this amazing salt ash mine in Germany where they'd, so it was kind of incredible. We were sort of driving underground for kind of hours, it seemed. But then they discovered this cave which had very little disturbance on it. And the crystals, so these crystals of salt, which were cubic, very often there's too much disruption of nature, the randomness comes in. So although on microscopic level you'd see a cube, but actually how it forms is pretty rough and ready. But this cave had managed to preserve the growth of these crystals, such you saw perfect, cubes of this size of salt, because the kind of randomness of nature hadn't sort of disrupted the growth. So you saw the micro scale suddenly being grown to kind of macro scale. Oh, question over here.
Yes. If I remember correctly, you talked about discovering fractals in the 20th century. You didn't say invented.
Ah, yes. So this is, of course, this tension between the idea of discovery, which you feel like, well, it's somebody else has already created it and I'm digging it up, or creating it or inventing it, that I'm the one who brought it gave it life. And I think mathematicians have a very schizophrenic relationship with this. And I think it's very different in a way from the sciences. I think there is a difference. I'm able, the things that we come up with that in science have to match the reality of the world around us. But I have freedom actually to make things which do not have physical reality. So we have many different sorts of geometry. One of them will be the geometry of our universe, but I'm interested in those geometries even if they aren't. Whilst for the sciences, once something doesn't fit science, then it kind of gets thrown. So I think that's already giving you a hint of there's more creativity in mathematics, because provided it's self-consistent, it's sort of an interesting world, it's a possible world, and it's not maybe our world. I think that I sometimes compare it to one of the other characters that crops up a lot in the book is Borges, one of my favorite short story writers from Argentina. He got very interested in the mathematics of the early 20th century, the ideas of new infinities, of multidimensional space. But he has a lovely book story called The Library of Babel, which is about a library whose geometry is really interesting, because he basically builds in the story the surface of a four-dimensional torus, and he really didn't know he was doing that. But it's in the book, in the library, is a copy of every book that it's possible to write. All the different combinations, a bit like all the Mozart waltzes. And the librarian gets very excited because he says, oh, this contains every book, it's got everything. And then you realize it contains nothing, because nobody's made any choices of the things which are interesting. And my feeling is that tension of discovery and creativity is that, in a way, we have all the possible statements about numbers and geometry, and there is a sense of, which are true, there's a sense of discovering that truth, but the creativity comes in, but which of those, that's the creative and somehow the invention of why am I picking this one out as another one? And I feel that's where that tension lies. It's almost like, well, you could think of music like the Library of Babel. It's all the possible notes on the piano, for example, the number of, there's only a certain number of notes that we can listen to, in fast sequence. So that gives parameters which says there's a finite number of pieces of music. So you could say Mozart discovered Don Giovanni in that kind of parameter space. So I sort of feel that the mathematics has that feeling as well. We can't make things true if they're false and vice versa. But within that, there's just a huge realm of choice that the mathematician makes, which is, I think, why we feel like we're creating the thing. And it was, although technically it was there before we brought it out, it's our act of bringing it out which feels like the invention and the creativity.